If you've ever found the slope-intercept equation for a line, you've done functional analysis, which is a method for finding the relationship between dependent and independent variables in a data set. If you graph the results of your experiment and they look linear, draw a line of best fit, find its slope, and then write down the equation in y equals mx plus b form, and you are done. At Punahou, in our physics department, we generally ignore the y-intercept b, though you may not. If your graph doesn't look linear, you can still use functional analysis. You will just need a few extra steps. For simplicity, we will limit our data to one of these four possibilities, either linear, inverse, power, or root. Any Algebra 2 student can tell you what these names mean. Linear means y is directly proportional to x. Inverse means y is proportional to 1 over x. Power means for us y is proportional to x squared, and root means y is proportional to the square root of x. So when we do functional analysis, if we see that the graph takes the shape of an inverse, we'll calculate a new variable which computes 1 over x for every value, and then look at the graph of y versus that new variable. Doing so should return us back to step 1, where we can have a direct proportionality, find the slope of it, and write down the equation. Let's look at how that works now. Suppose you have a data set like this. When you graph your data, you get a curve shaped like this. You need to, first of all, identify the shape of it. Is it linear, inverse, power, or root? Okay, you answer that question for yourself. Okay, what did you get? Good, it's an inverse shape, so that means that pressure is proportional to 1 over volume. To find the relationship between pressure and volume, we'll calculate 1 over volume for each value and then graph pressure versus 1 over volume. I'll do that now in LoggerPro. All right, this is the LoggerPro data software we use in Punahou Physics. I have my independent variable is volume, my dependent variable is pressure, and this is a graph that shows both of those. I'll scale it a little bit so that you can see the values better. So I agree that it looks like an inverse, so I need to calculate what that means. That y is proportional to 1 over volume. Pressure is proportional to 1 over volume. So I'm going to calculate 1 over volume for every value of volume by entering a new calculated column that I'll name 1 over volume. I'll give the short name 1 over capital V. Units are 1 divided by meters raised to the 3rd power. And the equation is 1 divided by the variable volume. Now when I click done, that should pop up a new data column. It looks like it's shown up in the wrong place, so I'm going to find it there, and there it is. So that's 1 over 0.1 is 10, 1 over 0.5 is 2, and so on down the line. And then to make that display on my graph, I'll click on the x-axis label like that, and I get options for all of the variables that exist within the data table. I'm going to select 1 over volume, and it automatically graphs it and scales it accordingly. And then I'm going to just rescale that graph slightly so that you can see all the data points. It does look linear with 0 y-intercept. So now to complete the functional analysis for this set of data, I click on linear fit to find the line of best fit. There it is. It says the slope is 4 pascals divided by 1 over meters cubed. Okay, so I can use that to write down an equation that says pressure is equal to this slope with its units times 1 over volume. So what that looks like, what does that look like? Let's take a look back here, and I have it typed out for you. Okay, pressure equals 4 Pascal times meters cubed divided by volume. And that's functional analysis for our sample set of data. Now, there are a few things that can hang you up along the way. One common mistake is to think that a square root graph is linear. So here's a sample set of data for a square root graph. You can see I can do a line of best fit for that, and it does look like most of the points are on the line. But two things that give this away. Notice, one, there is a significant y-intercept, and two, the first and last points are below the line of best fit, and all the rest of them are arcing above it. So really, a better fit for this data is a square root. Also, a lot of physical systems, it doesn't make sense for there to be a y value when x is 0. Like, for example, if you have a pendulum swinging back and forth and x is the length and y is the period of the pendulum, it doesn't make sense for there to be a 0 length pendulum string that has a 6-second period. It should go to 0, 0, and a square root graph would follow a trend that makes it do that. Okay, so that's a quick overview of functional analysis. I hope it helps you to learn what you need to do.